In this video we're going to look at special right triangles. These angles, 60 degrees, 30 degrees and 45 degrees, come up quite a lot in I guess trigonometry textbooks and in SAT questions, things like that, basically because they're easy to deal with, and in the past quite a lot of technical drawing materials were based around 30 degrees and 60 degrees and 45 degrees. In any case, we still have to remember what, for example, the sine of 45 degrees is and all these kinds of things. First things first, let's just look at these two triangles. This triangle up here has an angle of 45 degrees. If it has an angle of 45 degrees, that means that this angle here is 45 degrees, which means that this side and this side have to be the same. If we say that this side and this side are both 1, then using Pythagoras, you get 1 squared plus 1 squared, which should be 2. And then the square root of 2 would be the length of this side here. So if you want to get the sine of 45 degrees, it would be the opposite over the hypotenuse. In other words, it would be 1 divided by square root of 2. And that's what we have right here for the 45 degrees. It's 1 over square root of 2. If you multiply top and bottom by root 2, you'll get root 2 on the top. Root 2 times root 2 on the bottom gives us 2. So you'll sometimes see sine of 45 degrees written like this and sometimes like this. In the same way, the cosine of 45 degrees is going to be the adjacent over the hypotenuse. It's going to be the same thing. It's going to be 1 over root 2. And then the tangent of 45 degrees is going to be the opposite divided by the adjacent. So it's 1 divided by 1. That's a nice easy one, and one that we should remember. The tangent of 45 degrees is 1. Now, this drawing over here is a little bit more complicated. Basically, it's an equilateral triangle with each of the sides being 2, 2, and 2. However, we've split this triangle up into 2 equal triangles by putting a line through the middle. If we put a line through the middle, then this distance here, instead of being 2, is just 1. We have a right angle there. We can use Pythagoras with this triangle, with the 1 and the 2, to get this side here to be square root of 3. It's just 2 squared minus 1 squared, that's going to be 3, and then to get the length of this side, take the square root of 3. Now what's interesting is that in an equilateral triangle, the angles would be 60 degrees, 60 degrees, and 60 degrees. But of course we've halved this angle here, so now it's just 30 degrees there. Now, looking at this 30 degrees column here, if we want the sine of 30 degrees, this is your opposite. This side here is opposite, this is your hypotenuse. So the sine of 30 degrees is 1 divided by 2. And we have that right here. The cosine of 30 degrees, the cosine of 30 degrees is going to be the adjacent over the hypotenuse, and that's going to be root 3 over 2. And the tangent of 30 degrees, again, it's the opposite over the adjacent, so 1 over square root of 3, and that's the tangent of 30 degrees. You'll notice that it's possible to rewrite 1 over root 3 as root 3 over 3. Okay, now that I've shown you how to get the sine, cosine and tangent of 30 degrees, what I'd like you to try is to in here, put the sine of 60, cosine of 60 and tangent of 60. Pause the video and then come back once you've finished. Okay, what you should have when you do that, sine of 60 degrees, sine of 60 degrees is going to be this side divided by this opposite over hypotenuse. This side is now opposite the 60. Okay, so you should have something that looks like this. Cosine is going to be a half, and tangent is going to be, instead of root 3 over 3, it's just going to be root 3 over 1. And the last thing, you have to use your imagination a little bit here, but if you imagine this angle here getting smaller and smaller and smaller, in other words, we had a triangle that was going to look like this. So you'd imagine what was happening to the opposite side. That opposite side there would be getting smaller and smaller. So the opposite would be close to 0, so you'd have 0 divided by something. So the sine of 0 is just 0 degrees. The cosine, you would have to be doing this side here divided by a side that was very, very close to the same length. So 1 divided by something that was very close to 1. Once this angle here gets closer and closer to 0, it becomes actually 1 itself. And then the tangent, well, the tangent is just the opposite over the adjacent. So the opposite over divided by 1 again is going to be just 0. And then if you imagine this angle here getting bigger and bigger, so this time instead of being sort of small like this, it would be much, much bigger. So the length of this side here would get bigger and bigger and bigger as this angle here gets bigger and bigger. So instead of the side being here, it'd be sort of way up like that. It'd go up, and that side would be very, very long. So if you imagine what sine of 0 would be, what sine of 90 degrees would be. Sine of 90 degrees as this angle here gets closer and closer to 90. This side here gets closer and closer to what the hypotenuse is. Right? This side gets much, much bigger. This side also gets much, much bigger, but they become almost the same value. And so sine of 90 degrees is actually equal to 1. The cosine of 90 degrees would be this side here, the adjacent, divided by this. Since this side here is getting much, much, much bigger, you're going to have 1 divided by a really large thing. So 1 divided by a really large thing, it's going to get closer and closer to 0. And then the really frustrating thing is the tangent, because what you're going to have is this thing here, which is going to be effectively infinitely long if this angle here is 90 degrees. So infinitely long divided by 1 doesn't really work. Right? Opposite divided by adjacent doesn't really work because this is kind of infinite here. And so if you do that, you just get what was known as a domain error, that you can't actually get the tangent of 90 degrees.